What did I get?
Perkins, you know the game?
Queen.
Oh yeah, you did have the doctor's appointment.
He basically did
Colin.
x-rays and said, I have no idea what's wrong with you.
I just need to
It's like,
understand.
good. So I'll send you to an orthopedic guy. Okay, great.
More money. That's all that happens.
Yeah, that's all that happened. And he gave me some different painkillers.
This episode of Physics Honor is brought to you by Painkillers.
Berg's Perkins.
That's actually, that was a muscle relax. Okay, start that up.
Good start.
We're going.
Okay,
So chill.
look. Let's settle the pitcher-catcher debate, okay? What's the role of the pitcher in terms of momentum? What's the initial momentum of the baseball?
Zero.
Zero, right?
Yep.
Zero. So on a momentum time graph, the pitcher over some period of time is going to change the momentum of the ball, right?
Yep.
And he's got to start back here
It's
and
not
go through
funny.
this whole
It isn't
windup.
funny.
Shh. Shh. You asked, I'm going to explain. Okay? So this is the windup. This is the throwing action. True? True? So this is the act of throwing. Okay? Now at this point, the pitcher lets go of the ball. Is he exerting a force on the ball any longer?
No.
No. The ball is flying through the air with the greatest of ease. So over a relatively short distance, what's going to happen to the momentum of the ball? It's going to stay constant. Technically, it will increase a little bit because it's following, but let's just assume this is going to stay constant. So it's going along like this. So at this point, this is when it leaves his hand, because there's no other force acting on it at this point, right? Okay? So the momentum's going to remain constant. So it's going along at this point, the catcher catches it. Okay? So as soon as it comes in contact with the catcher's glove, what's the momentum going to do?
Decrease.
It's going to go down. So let's say this took, just to make up some numbers, let's take like on a throwing motion, maybe a half a second. Okay? Just to make up a number. Okay? So it took about a half a second. You know, if I've got this golf ball, here it is, right? It's going to take me about a half a second to go through that motion. Now, I'm going to throw this to Shively, okay? I won't throw it that fast, right? So, when Shively catches it, did it take him the same amount of time, more time or less time, to stop the ball? Less time, because you just have to go like this, right? Okay? Where I've got to go through this whole throwing motion. So if it took me a half a second to throw it, what's going to happen to the time on the catcher? It's going to be less. So instead of a half a second, let's say it's a tenth of a second. Okay? So remember, impulses change in momentum. So this is important. Which one of us imparted the greater impulse on the ball? Me, Shively, or was it the same?
It's the same.
It was the same impulse, right? Because it was the same change in momentum. But who exerted the larger force? The catcher did, because that change in momentum is going to occur in a shorter amount of time. Yes. It isn't the change in momentum, it's the rate of change in momentum. Vaughn, did that settle the argument?
Yeah.
You sound disappointed that I settled the
Well, I
argument.
was righter than Mary was.
You were righter. I was righter.
I think.
Okay. Great.
Number 5. Yeah.
Yeah.
I said pretty much that it was like a dampener or a spring, but I don't know if that was correct. To reduce the force exerted on the parts.
Look at this graph. What are you trying to do with time?
Increase.
By increasing the time, what are you trying to do?
Increase the rate of change.
Which reduces the... Yes, there you go.
Okay.
Now, let's talk about problem number 13. Okay? Let's make sure everybody's cool with problem number 13. Just in case some of you have children. So, it used to be, this is a scary thought. So, there is a time in history what we call BW, which stands for before Walmart. okay?
Whoa, whoa,
Whoa. Worse yet, there is a time BC, which is before cell phones, okay? We'll talk about that later.
VO before Oreos?
Oh, well, oh, yeah, that was horrible. Thank God I didn't live in that
Is there a
time.
BB?
I'm bad enough I survived the BC time and the BW time. It's both
That's a
kinda-
few eons back.
What's
up?
Is there a time BB before Berg? You said a few eons.
Alright. No need to snitch on the
Hey,
man.
that's either calling you an immortal being or it's mean. Which one would you like better, mean or immortal being?
Let's go with immortal.
All right, that's what I meant.
Okay.
I got you back, man.
Yeah, I see that. Okay. All right. So in this time before Walmart, there was a time when kids like weren't strapped in car seats. Like there was a time like you could not even buy a car seat. Okay, like they didn't exist. Okay, literally, like they did not exist. And so like I remember when I was a kid, grew up in Cheney, and I'd be riding into town with Dad, and he had like, you know, a truck with a big bench seat in it. And I was shorter than him, and I would literally stand, because I went to CI, so I would stand up right beside Dad, no seat belt, nothing. And we'd just be driving down the road, and I'd be standing up beside Dad in the truck. And whenever Dad would hit the brakes, he'd put his arm out to keep me from flying forward. Sometimes he'd push me, but for the most part, you know, Dad would try and stop me. And that's how everybody grew up. I mean, up until like the late 1950s. Seat belts were like optional. Like you had to order seat belts in your car. Like that wasn't mandatory equipment. And so there certainly wasn't child restraint seats and everything else. And so you could always tell moms when they drove. Because even if they didn't have a kid in the car, when they hit the brakes, they would instinctively take their arm and put it out like this.
Mom arm.
It was the mom arm. Because it was just like Pavlov's dog. It was like, oh, you hit the brakes, boom. You put your arm out to stop Timmy from flying through the windshield.
Old Tim.
Huh?
I said old Tim.
Old Tim. Now, so what happens is that the physicists got a hold of this and said, whoa. Let's look at this. So, if you look at what's happening on 13, you're moving at 10 meters per second, which really isn't even that fast, okay? I mean, you're moving at 10 meters per second. You know, a world-class sprinter can run this fast. So this isn't like highway speeds, okay? And you're going to stop in 0.35 meters, which is about like yay, okay? So again, this isn't like a complete boom where you're just going to stop all of a sudden. Okay, there's a little bit of distance involved. So if 13A is wrong, everything else is going to be wrong. So your answer to 13A should be 0.07 seconds. Okay? And you've got to use this distance. There's any number of ways you can do it, but what you can't do is just take distance and divide it by velocity, because the velocity is changing because you're slowing down. Okay? So your answer to 13A is 0.07 seconds. Okay? So you're stopping this kid in 0.07 seconds. And so then on B, you're trying to find the force required. Okay? So your answer to 13B should be like 10 to the third newtons. Okay? Pretty big amount of force. And so then what I'm asking you to do to get your answer for C is to take your answer from B, divide that by 9.8 meters per second squared. Because what you're trying to find is the equivalent amount of mass you would have to lift to generate that much force. So your answer to 13C should be around 300 kilograms. Okay, that's an ish. Now, each kilogram is about 2.2 pounds, which is about 660 pounds. So what the physicists did is they said, Mom, love y'all to death, y'all have superpowers, you're wonderful people, but you're not going to stop this kid from flying through the windshield. I mean, that's just the cold hard reality of it. You are physically not going to take your arm and have to provide the equivalent amount of force of taking one arm and lifting up 660 pounds. It's not going to happen. And that became the whole driving force for child restraint seats, and that's the whole basis of it. It's like, Mom, love y'all to death, you're not stopping Timmy, okay? It's just not going to happen.
Timmy gone.
Well, yeah, Timmy goes by. No, when you get to 14, there's two different ways you can work 14. And you'll get the same answer either way. So when you drop this ball, is there a force exerted on the ball? Did you seriously shake your head no? So if I drop this ball, wherever it went, there you go, yeah. So if I drop this ball, is there a force exerted on the ball? Yes. And what's the, and what is that force? Can you find the value of that force? Yeah, oh, Fg equals mg. Is that force going to create a change in momentum? Yeah. And change in momentum equals force times time. So this is going to give you the value of the force. Now, you also know how far it falls, right? And so one option is you do distance equals 1/2 at squared plus v naught time. Initial velocity is 0. You can find the time from this, put that in there. That's one way you can work the problem. Let's take force times time equals change in momentum. It's cool. The other thing that you could do is go old school, v squared equals v naught squared plus 2ad. Okay? That's your other option that you can do. Find your final velocity, multiply that by the mass, boom. There's your momentum that way. Okay? Doesn't make any difference. You're going to get the same answer with your personal preference thing. Now, what you should see is that some of these answers should be negative. Okay, so if you look down your assignment and you have absolutely no negative answers, something has gone wrong. Now, just don't go through and randomly start putting negative signs on some of your answers. Okay, that would be bad. Okay, that would be bad. If they don't generate the negative answers, you've missed something. Make sure on that force time graph that you kind of labeled everything so I know exactly what everything is. Okay? Just don't randomly draw it and think that I'm going to know what it is. Any questions? Once, twice, Vonda?
Okay, number 6, letter B.
Yeah.
Yeah. Or like the second part with the change of velocity.
Yep. So, Vonda, what do you have for your answer for part A?
The 60.
Newton seconds.
Yeah.
It's a beautiful answer, right? That is. So, change in momentum, right, equals mass times delta V. True? Did you find the change in your momentum?
Okay. Yeah. Yeah.
Yeah.
And you divide it by the mass.
Yeah.
Okay.
Yeah. Thanks, Bo. Okay. Now, but here's the interesting answer on part 6 on that change in the velocity, and that's going to be 20 meters per second. Here's the deal. That's just your change in your velocity. That could be going from 0 to 20. It could be going from 10 to 30. Okay? You don't know exactly what the change, what the numeric value is in terms of where you start and where you end up. You just know that's your change in your velocity. Okay, that's all. It could be going from 0 to 20, but it could be going from 60 to 80. Doesn't make any difference. Okay? We're good? Going once, going twice? Sold. Get those handed in.
No, what I want to do is not listen to you and do my stats.
Really?
That was really mean.
I know, but it's too next watch. I don't want to. But I only
Maybe
have,
you
like,
should have
4
done it
problems.
yesterday.
Okay, but listen, half of the problems are in the back of the book anyway, so.
You have rabbits? That's not. He won't care if you
I know,
turn it
he
in
doesn't
late.
care. That's why I'm not worried about it.
This is why I hate textbooks.
Why? Oh,
Because the answers are in the back.
How do we know Bergkamp's not teaching us false stuff if we don't?
Okay, but you give us like 20 problems. Do you want to see how many problems? Like,
Physics doesn't.
Because we've done the calculation. But it's not like one night you have to do all that.
Okay, I know he's
all
right.
these problems. Like, no, thank you.
Everything about stats, it sucks.
Yeah.
It's not that bad.
Okay. So let's talk about something relevant, which is science. Okay.
Wait, what's worse, stats or biology?
Ooh.
Stats.
Odds-on favorite. I don't know. That's
Biology's
I say stats, because
Biology,
biology can be
at
interesting.
least stats doesn't smell bad or potentially give you like some kind of weird.
Okay, but it's
disease.
not interesting at all.
Biology.
Biology has relevance.
I was
Oh, yeah.
pretty good.
Biology's
BBC
pretty fun.
documentary series yesterday
Except in
about
biology, you
Africa.
actually.
On what channel?
BBC. It was on Netflix.
Is it just called Africa?
Nova?
Nova.
Was the series by Nova?
No, it's BBC.
I don't know.
British-
Free State,
British.
Matthew McConaughey.
British Broadcast Channel.
David Attenborough.
No,
Oh,
the-
yes.
Is it just called Africa?
Yeah.
I watched
On
that.
Netflix?
I love
British.
documentaries.
British.
Okay, anyway.
You watched WWF Most Dangerous Animals? Yeah, I love that show.
Okay. So, when you look at the conservation laws that exist in science, two of which you've already used if you take at least Chem 1, okay? The first one is law of conservation of mass, which basically says matter cannot be created or destroyed. And that's what allows you to balance equations. Okay, if you have 4 hydrogen atoms on one side, to balance it, you have to have 4 hydrogen atoms on the other. If you have 2 oxygens, you gotta have 2 oxygens, okay? Now, how that plays out, and this is why you throw energy, because energy used to be a part of this, but Einstein kind of combined the two into his famous equations that E equals mc squared. We'll talk more about this once we get into energy. And so basically, that mass is the difference between like the mass of the reactants and the mass of the products, which doesn't play out in a normal chemical reaction because those are the same. Where this plays out is what fuels the sun. So our sun basically emits a tremendous amount of energy because in the sun you're taking 4 hydrogen atoms, combining them into 1 helium atom. And that small mass difference between the 4 hydrogen atoms and the 1 single helium atom gets converted into energy. And that gets plugged into here where you have E equals mc squared. Now, you have c, which is the speed of light, 3.0 times 10 to the 8th meters per second. Well, when you square that, that gets you 10 to the 16th. So it doesn't take very much mass at all to generate a tremendous amount of energy. So this process here is why we have the sun. So where that's cool is that goes even harkens back to the Big Bang. And okay, you had pure energy. Well, that amount of energy that existed dictates the maximum amount of mass we can have in the universe because they're conserved. So if you start with a certain amount of energy, no matter what, how you change that, whether that's mass, whether that's energy, that's like a fixed amount, and that's all we have in the universe. Now, you can also have conservation of charge. So if you've ever done net ionics in Chem 1, where you have like an Fe2+ ion combining with 2 hydroxide ions to form the insoluble FeOH2, okay? That also has to be conserved. So those are the 2 ones that you've kind of dealt with so far. Today we're going to deal with linear momentum, and then Thursday we'll deal with angular momentum. But basically they all have the same form. It's just insert the blank. So if you're talking about mass, it says matter cannot be created or destroyed, or whatever matter you have at the beginning is how much mass you have to have when you get done. So the same thing is going to be true of linear momentum. So however much momentum you have at the beginning of the system is however much momentum you have at the end of the system. That's it, okay? So basically they all have the same form, you just insert different things. Angular momentum, linear momentum, charge. All of these are the 4 great conservation laws of science. So here's how this plays out. And this is one of those deals where you all intuitively understand this. I just have to convince you that you do. So we're going to the back of the room, and we're going to have 2 little green carts, okay? And one of them is going to have like a compressed spring, and they're going to be sitting there, and I'm going to hit the spring, and we're going to see what happens. Now, here's the beauty of every momentum problem, is that they all work the same way. Where you run into trouble is if you try and shortcut the process. If you don't shortcut the process, you're going to be golden, okay? Where you run into trouble is if you try and get cute and go, I don't need to write that out. Train wreck, okay, whatever. So here's the deal. So I'm going to have card A and I'm going to have card B, okay? So what are the 2 things that determine the momentum of a system? Mass and velocity. So here's how this system starts. You go, okay, the momentum of A plus the momentum of B has to equal the new momentum of A plus the new momentum of B. Or the sum of the momentums before has to equal the sum of the momentums afterwards. Doesn't matter. They all start the same way. If you've got like a rock and a boat, okay, a bullet and a gun, it doesn't make any difference, okay? They all start the same way. Write it out as the sum of the momentums, and then go from there. Now, in this situation, I need the mass of A, times the velocity of A plus the mass of B times the velocity of B is going to equal the mass of A times the new velocity of A plus the mass of B and the new velocity of B. So how all of these problems start. Now, the beauty of this is the two cards are at rest. So what's the initial momentum of the system? 0. Why?
No velocity.
Yeah, and everything is at rest, right? So what this means is that initially, in this particular problem, the left side of the equation is equal to 0, okay? I got no motion, I got no momentum, okay? Nothing's happening. I got no momentum. Now, what does that mean in terms of the momentums over here? They have to add up to 0, okay? Now, this is important. That doesn't mean that I can't have momentum over here. Okay, that's not what I'm saying. I'm just saying that the two momentums have to add up to 0. So, what's the only way these momentums can add up to equal to 0? If they are? Yeah, equal and opposite. Okay? It could be positive 4, negative 4. It could be positive 6, negative 6. Doesn't make any difference. The only thing you have to know is that these momentums are going to be the same. Okay? That's the only thing you really need to worry about. Now, what that means is, in terms of mass, is the mass ever going to be a negative number?
No.
Why? Why?
You can't have a negative mass.
Why can't you have? Why can you not
Because
have?
then it
Negative?
wouldn't exist.
Everything is greater than 0 as far
You're both right, but what type of quantity is mass? Scalar or
Scalar.
vector?
Scalar quantity.
Scalar, because it doesn't make any sense to give it a direction. Okay? Hey, it's 1 kilogram mass. That's it. So if your velocities, if your masses can't be negative, what's the only thing that can make it negative? Velocity. Ah, okay. Now, keep that in mind. Let's go back and see what happens.
Matt, you're pushing around.
You gotta push in the chair.
You're pushing around our guests.
Oh, sorry.
You should just leave. Feel my dad. I think he got me a cigar. You're down here. Well, there's a thing right here.
You have no idea what you're talking about, Olivia.
Look.
Okay,
No.
Okay, that's
Olivia's
biology.
insane. You want to hold this?
I don't
No,
know.
I don't.
I don't know what it is, Virgie. I'm probably
I mean, if you want to,
die.
I'll hold
We all will.
it. It's just you're right in the middle.
Yeah.
It's just a statement of fact. I mean,
I know.
we could lie and say it's not true. Okay, are we
Every day
on?
you're
Yeah.
alive, technically you're dying more
That's
and more.
not a bond.
Okay. You're gonna be fine. You're going. It's a long way from
I got on
here.
kid's side.
Can I scan it?
All right. So right now, what's the momentum of the system?
0.
Now, so when I hit that spring and release that plunger, what do you know is going to happen?
We're gonna go different ways.
Why do they have to go in opposite directions?
Because every action has an equal and opposite reaction.
Hold on.
They don't, yeah.
What's the momentum of the system?
0.
Zero. Afterwards,
They gotta be equal and opposite.
yes, because that's the only way they can add up to
0.
0. So if I hit this, right?
Whoa.
Whoa.
Whoa. Okay?
Again.
Do it again. Okay? Kind of caught that one. Let's try that again.
Did a little bit.
I did a little bit.
But, well,
Okay? Now, so why would it be a violation of the law of conservation of momentum if I hit that and then they both started going in this direction?
Because it doesn't. You said
Because they would not add
It
up
would
to
not have a
zero.
zero momentum.
Yeah, well, I would have created momentum. Because then if you define this direction as say being positive, because that's you're always right. So if they both started going in this direction, then the momentums won't add up to equal to zero, and I've created momentum. The same thing would be true here if I hit this and they both started going in this direction. So in this situation, here's what's important. Everything's going to be at rest, okay? Everything is at zero. That means everything still has to add up to equal to zero. Now, you can also change it a little bit. And we're trying to do this moving. So if it's moving, okay, if the system is moving like this, the same thing has to be true. The only thing different is that now everything isn't going to add up to equal to zero. It's going to add up to whatever momentum I have to begin with. So if it's moving, and I hit it, now everything still has to add up to whatever momentum I had to begin with. So don't think, oh, every momentum problem starts at zero. Okay? It doesn't. You just have to have everything add up to that initial momentum. Now, what if I take a 1 kilogram mass and I put that on this one and do the same thing?
Mass is different. Oh, I guess it's
The one on the red will go faster,
Why?
because since it's got a smaller mass, it has to have bigger velocity to compensate in order to get back to zero.
Okay. So here's the deal. So when I hit this, again, go back to this idea. What's the initial momentum of the system?
Zero.
So everything still has to add up to
Zero.
Now, initially the cars were identical. They left at the same speed. Okay? With this one,
That's a slow move.
okay? Now, but this is moving slower. But which one had more momentum?
They had the same.
They had the same momentum. But this one had more mass, so it had to be moving slower. Now, Madeline actually said something earlier in terms of Newton's third law. Okay, so what's Newton's third law? What's equal and opposite?
Every action has
Every
an equal
action.
opposite
Yeah, every action has an equal and opposite reaction. Every force has an equal and opposite force, right? So the other thing why I couldn't do this and they both move in the same direction is that would also be a violation of Newton's third law. Now, notice that these aren't laws. These are laws. These aren't suggestions as well. It might happen. I don't know, maybe, whatever. Okay? No, these are absolute laws. So if I did this and they both moved in the same direction, that would be a huge violation of Newton's third law, which generally doesn't happen very often at all, actually. Okay. Now, what if we did this? What if I keep this one at rest and I move this one into it? Okay? Now again, what's the initial momentum of the system not going to equal? Zero. So now, when this happens, what do you know has to happen to this cart? Okay? Now, is it going to have the same momentum as this one does?
Yes.
The total momentum will be the same.
The total momentum will be the same. Because if this one has the exact same momentum as this one does, okay, if you think this through, if this one took all the momentum from this one, what would this one have to do?
Stop.
Stop, okay? So it doesn't stop. Now, but there is an interesting thing that happens. Look what happens to the gap between them as they roll. It increases. Why?
Because it's moving at a faster
This
velocity.
one's moving faster than this one is because it has less mass, so therefore it has to be going faster, so that gap is going to get bigger. Okay? Now, what if we did this? What if we took this one and slammed it into here? So this one actually moves backwards. But again, so anytime something changes direction, what has to happen to its velocity?
Must change.
Yeah, so if you define this direction as being negative, right? When this one came in and hit it, so it had to stop it, go from positive velocity to a,
Negative.
which means it had to go through
Acceleration.
Yeah. It did have to undergo an acceleration. But what velocity did it have to go through to change direction? 0. Okay. So, you can have situations where you can have both of them moving. Okay? All right?
Oh,
Whoa. Now, if you do this one, right? So, there's a whole bunch of different ways this can play out. Okay?
See you later.
Woo! But we're off to the races. So, but here's the deal. No matter what happens, okay? No matter what happens, if this one's going like really, really fast, okay? Notice that one bounces back. No matter the situation, what do all of the momentums have to add up to? No.
The initial.
Just whatever the initial momentum was. Okay, that's all it has to add up to. Now, you can also have a situation like this. Got one card here. Here we go. Here we go. Oh, hold on, I'm the wrong way.
Oh.
Okay? Now what happened? So now, look what immediately happened.
Stuck.
They stuck. But what happened to the velocity? Began to slow down. Oh, because mass increased. So this is the kind of the California hippie thing. You have one person, right? And they're going to run into somebody else, and they're going to move in together, and then they're going to move off. Okay, so this is like what I call the California thing. And I know, oh, this is just California, but they started the train festival. So you got this, boom. So immediately, what happens to the velocity? Slows down. Now here's what's important. Okay, listen to me. Here's what is important about, and I'll refer to it as the California move. Okay. So in the California move, what do you notice about the velocity of each cart? Is it the same or different for each cart?
One goes down, one goes faster, but they both end up the same.
Yes. So here's what's important. When you have the California thing happening, okay, like this, two things are going to happen. It's going to slow down, and they're both going to end up moving with the same velocity. And they're also going to have the same sign as whatever the moving cart is. So if this is like negative, if you define this direction as being negative, then they're both going to end up with negative velocities, but it's going to be less than what you started with. If you define that direction as being positive. Now here's what you cannot have happen. Is that you can't have your velocity change sign on a California roll. So it isn't like we're going to put these two together, they're going to get combined, and then they're going to start moving in this direction. Okay, which would be cool, but it's not going to happen. Because I can guarantee you, if I did that, even though y'all haven't studied law of conservation of momentum, if I did that and they started moving in that direction, y'all would be going, witchcraft! Okay?
Sorcerer.
Yes, because you intuitively understand, oh, this is what should be happening. Okay? Got it? Good? Grand?
Let's head back.
back we go.
Back we go.
Thank you.
I'm telling you.
Red and now it's it was the etiquette lab.
Big E's.
The salad was surprisingly good.
What sort of dressing is this?
I don't remember. I made
You don't remember what was in it?
it. Lettuce,
No, in
Cheese.
dressing.
cheese,
There was cheese.
croutons,
There was cheese in the dressing.
and salad.
What was the dressing?
I don't remember. Instead of bomb.
Stop saying that. You can't say that. I mean, it's not an airport, so we can.
Well, yeah, if you yell bomb in the middle of the lunchroom, you can tackle.
Oh yeah, bad things are gonna happen.
That's stupid.
But this is Berg's physics room. He doesn't think we're
Sounds like something Joel would do.
yell bomb in the middle of the.
Yeah. But he'd be like this. He'd be like, "This is the bomb,"
Oh yeah.
but people would only hear the bomb part.
This. Yeah. And then.
But it would be really funny to see him get tackled.
I would tackle him. Giving you explosives on you. You really just said those words, huh? Yeah. Just quiet enough that they can hear.
Okay,
so distorted and trash. I can't hear it. What? Bad.
Okay.
I hate that song. Stop.
Nothing. So my eyes look dark. Like around his eyes. Does it?
Yeah, it kinda hurts to look at.
Oh,
Alright, Casper.
Maybe go sleep at night.
all right.
Sleep
That
at
works.
8:30.
Okay.
Sleep
so
earlier.
Here's the setup.
Dummy.
So there's a couple of things about momentum problems. First off, they're usually set on frictionless surfaces because friction just annoys things, okay? So a lot of times you'll see momentum problems set like on ice rinks, okay? Because it's much more of an idealized situation. So unless you're specifically told to worry about friction, don't worry about it, okay? So it's like an idealized world. Just like whenever we talk about acceleration due to gravity, we always assume that it's in a vacuum and it's always accelerating at 9.8 meters per second squared, okay? It's an idealized world. In reality, it's not going to happen. So here's the setup. So I got a bullet with a mass of 15 grams, traveling at 252 meters per second, and it's going to hit this block of wood that has a mass of 1 kilogram, okay? So there's three things that can happen when that bullet hits the block of wood. What's one of them?
Could bounce back.
It could bounce back. If it was really hard wood and the bullet was like a rubber bullet, okay? It could hit and it could bounce back. That's a possibility. It could go through it. So the bullet could end up coming through the other side. Now, if the bullet does go through the other side, and if it hits at 252 meters per second, realistically, what's this velocity going to be relative to 252? Less. Okay, it might drop down to 100, something like that. Okay, it's certainly not going to be going out of there at 252 meters per second because it's going to lose some of that momentum to the block. So it could hit and bounce back. It could go through it, or it become
California movie.
or it becomes the California move where the bullet becomes embedded in it. So that's the one that I'm going to work, is I'm going to assume that that bullet becomes embedded within this block and it's going to move off together. So, literally, every momentum problem starts the exact same way. Don't shortcut the process. So in this case, I've got the momentum of the bullet. I hate this thing. Well, the other one kind of plus the momentum of the block, this one's back, equals the new momentum of the bullet plus the new momentum of the block. Okay? Don't shortcut this, don't shortcut this, don't shortcut this, don't shortcut this. Okay? These problems aren't difficult. Trust me. Now, in this situation, what's the initial momentum of the block?
0.
0. Why?
Because there's no
It's not moving. Now, the block could be moving towards the bullet, it could be moving away from the bullet, okay? But in this situation, it's not. It's just sitting there going, hit me, come on, hit me. So, that goes to 0. So, I got the momentum of the bullet, which is going to be the mass of the bullet times the velocity of the bullet. Now, here's what's important. I could get this number. I could take 15 grams, change that into kilograms, multiply it by 252, and I could get the initial momentum of the system. So here's one way that you can view that initial momentum of the system. Let's say I walk in and I've got $7 with me, okay? I got a 5 and a couple ones. But I got a hole in my pocket, right? So I walk into the system carrying $7. So I walk around, $1 falls out, Mary picks it up, okay? Walk along a little bit more, okay? Garrett picks it up, right? So, is there still $7 in the room? Yes. It's just changed forms. Okay, Garrett's got $1, Mary's got $1, I still got 5. But everything still adds up to 7. Okay, so that's what's going to happen here. So if I could actually get this number, then I would know exactly how much momentum there was coming into the system. I don't need it, but I'm just saying, if I found it, that's the maximum amount of momentum I could have at the beginning of the system, which means afterwards everything has to add up to whatever that amount is. All right, now over here. Now I'm going to write this all out, okay? I'm going to write this whole thing out. So this is going to be the mass of the bullet, the new velocity of the bullet, plus the mass of the block times the new velocity of the block. So this is like P prime and V prime. So the primes indicate that this is the new situation, okay? This is what's changed. Now, here is the full-blown mathematical equation. This works every time, every time. So this works if the bullet goes through, this works if the bullet bounces back. It works every time, okay? Every time. Now, conveniently, the bullet becomes embedded in the block. So here we have to make a decision. The bullet is embedded in the block, and they're moving in this direction, okay? This is what I showed you with the carts, right? Is the new velocity of the bullet 0 because it's embedded in the block?
No.
Yes.
Well, if the velocity of the
Is the new velocity of the bullet 0 because it's embedded in the block?
no, it's moving still.
Mary?
Yeah, it can move like with the block.
Okay, so visualize this, okay? Let's say Shively has one of those big medicine balls, right? And I'm sitting here, right? And he throws it to me, and I catch it, okay? And I'm sitting on my cool rollaway chair, right? So I catch the ball. What's going to happen?
And then roll back.
Yeah, I'm going to move back like this. But is the velocity of the ball 0?
No,
Why not?
because it's moving. With
Yeah, it's moving with me. So that's the most common mistake that's made, is that the ball set the new velocity of the bullet to be 0 because it stopped. It is stopped, but it stopped inside a block that's moving down the road. Okay? So that's the fundamental difference. So because these velocities are the same, because the bullet's embedded in the block, what can I do?
You can put them together.
You just make
You
it a
can
value.
pull out the mass.
Other rhymes with factor out.
Factor out.
I can factor out the velocity because it's the same. Now, this step is on the back of the lecture notes that I gave you all on Friday. Okay? I lay all this out on those lecture notes. The whole back side is dedicated to the conservation of momentum. And this is the step that I show you on the back side. So, here's what I'm going to do. I'm going to rewrite this as the mass of the bullet times the velocity of the bullet equals the mass of the bullet plus the mass of the block times d prime. Okay? Everybody cool? Got this. Life's good. Okay. Now, let's talk about this v prime. Is it possible when I find this v prime, because this is what I don't know, I'm trying to find the new velocity of this system. Is it possible for this v prime to be a negative number when I find it?
Not unless it was negative to begin with.
Yes. But if this comes in with a positive velocity, it can't be negative because that would mean that what you're saying is that here's this block that gets hit by this bullet traveling about 2/3 the speed of sound. And the block's going to hit the bullet, or excuse me, the bullet's going to become embedded in the block, and then they're both going to move in this direction. Not going to happen. Could this new velocity be bigger than 252 meters per second?
No.
Why not? What would that mean you created?
Momentum.
Moment.
You created momentum, right? Because you've increased the mass and you've increased the velocity, so wow, if you're going to violate the law of momentum, do it right. Okay, go big or go home. So there's two things I know about this v prime. It still has to be positive, it has to be less than 252. Okay? That's the deal. So, how am I gonna get this by itself?
Divide by the mass.
Divide. Gonna divide by the mass of the bullet. Plus the mass of the block, right? Now, I'm gonna point this out, and I don't mean to insult anyone's mathematical ability, but I have to do this or someone's gonna do this. Can I just cancel out the masses of the bullets?
No.
No,
No, why not?
parentheses.
Yeah, I'm adding here and I'm multiplying up here. That and the units would turn into a train wreck because you'd have meters per second divided by kilograms, and that doesn't equal meters per second. Okay? That's the other reason that you can't do that. Okay, so in this situation, remember the 15 grams. So we're going to take 15 grams. Now, I need to convert grams into kilograms. Do I multiply by 1,000 or divide by 1,000?
Divide.
I don't multiply by 1,000. Go, the bullet is like 15,000 kilograms, which would be like 15,000 of these. Okay? Be a lot. Don't do that. That would be bad.
One big bullet.
One of them would be bad enough.
They got a torpedo.
Kilograms times 252 meters per second. Okay? It's cool. And then we'll take 0.015 kilograms plus 1 kilogram. So somebody give me the numbers.
You have a lot of nice jackets.
Can I see that? Big jitter.
On the top is 3.78.
Huh?
The top is 3.78.
Yeah, I know the whole thing.
3.72.
3.72? Meters per second. Okay? Now, Ethan, did you get the top number by itself?
Yeah,
What did you get for that top number?
3.78.
3 point what?
78.
3.78. Now, here's what's important. What the 3.78 Newton seconds represents, if you think about this in terms of money, is like I walk into the room with $3 and say, that's all I've got. There's nothing more. So all I can do is redistribute that $3.78. Okay? Now, I might give, Max $1, I might give Grape $1, might give Shively $1, I'll give McGriddle 78 cents and go, here, go buy a McGriddle. Okay?
It's not enough for,
I know, hey, it's a story. But that's how much I've got to give out. Nothing more. Okay? That's it. Nothing more.
Let me get that.
Okay. So now, does the 3.72 make sense? Right? It's not going very fast. Right? So it isn't like we're going warp speed. I'm old and decrepit and I can run faster than this. Okay?
Really?
Maybe. Over short distances. Short.
If your life depended on it.
Yeah, if I was being chased by that hippo again, yeah, I could do it. That'd just be pure adrenaline.
I've never heard that story.
that's actually extremely scary.
Oh, yeah.
It goes like for,
Yeah.
responsible for like the most deaths
Yeah,
from
there's-
humans every year.
3 animals that almost killed me in Africa: rhinos, hippos, and elephants.
Wait, what happened with the rhino?
We'll talk about it. So,
I have a rhino right next to me.
the hippo was the one that came closest to killing me.
Those are scary.
Yeah, they are.
Those are
Hippos
the
kill more
deadliest
people
animals
in
in the world.
species than any other species in
Exactly.
Africa. Okay. So let's look at a velocity time graph. Okay, you're going, seriously? Oh yeah, oh seriously. So here's your setup. So here's the bullet, and it's going to start up here at 252 meters per second. That's where it's going to start, right? So this is when it's going to hit the block. So what's that velocity time graph going to do for the bullet? Going to come down like this, right?
Yeah.
But where is it going to stop? Is it going to go all the way to 0?
No, it'll stop at 3.72.
It'll stop at 3.72, right? Which is basically going to be right about there, okay? So it's going to stop at 3.72 meters per second. So this is the bullet line, okay? That's your bullet line across like this. Cool, right? Now, what's the block going to do?
0.
0.
It's going to start at 0 and it's going to speed up to
3.7.
3.72. Okay? So this is going to be the block line. So block's going to start at 0, going to speed up. Bullet's going to start at 250, going to come down. Now, after that time, when the bullet is sped up and the bullet is slowed down, the block is sped up. Now what's it going to do? Assuming that there's no friction, this is just going to be a horizontal line. Okay? Because now this is the California thing, and now they've moved off together. And okay, here we go. Now, here's the next question. Tori, did the momentum of the bullet change?
Yeah.
You say that with absolutely no confidence.
Yeah.
Yes,
Yeah.
you're right. How do you know you're right?
The velocity change.
Beautiful. Now, what do I need to find the change in momentum based upon change in velocity? I need three things. Mass,
Your initial velocity.
initial velocity, and
Final
the...
velocity.
Do I have all three of those?
Yes. We.
Yes. I can find the change in momentum of the bullet. True? Okay? So I can sit here and go, okay, I can roll this. Change in momentum of the bullet is going to be mass times delta V, right? So if the velocity doesn't change, guess what? The momentum doesn't change. But it did. So I got 0.015 kilograms. Now, the final velocity of the bullet was 3.72 minus the initial velocity of 252. So somebody take 3.72 minus 252 and multiply that by 0.015 kilograms.
Negative 3.72.
Negative 3.72 Newton seconds. Okay? So why is this a negative number?
Because it decreased.
It decreased and the initial momentum was positive. Okay? So I've lost some momentum along the way. Could I find the change in momentum of the block?
Yes.
Yes. Landon, how can I find the change in momentum of the block? Huh? No. Don't make this difficult.
I'm making.
You know the mass of the block,
Yeah.
1 kilogram. You know the final velocity of the block.
Yeah.
You know the initial velocity of the block.
Yeah.
Okay. So I can also find the change in momentum of...
Cut it out, maybe? I wanted to do it quick, but
How'd that work out?
not too good. Sorry about that, Barry.
If it's
So,
empty, can't you throw it in the sky?
I got
Water ball.
1 kilogram. And was that like a single-use water bottle?
No, it wasn't.
What?
Was that like a single-use water bottle?
No. No, that'll get used again.
I'm going to ban those from my room.
Do it.
Hear that, homies?
So, I got 1 kilogram. What's the final velocity of the block? 3.72. The initial velocity was 0. Oddly enough, I get... So what do you notice about the changes in momentum?
Does that?
They were saying, why?
Equal it up.
Because whatever momentum, remember, momentum has to be conserved. So whatever momentum is lost by the bullet has to be gained by the block. Okay? It's the only way it works, right? It is the only way that it works. So it's just like if I walk in here with $3.72, I can only lose $3.72. So you all collectively can only gain $3.72. Okay? That's it. I can't lose $3.72 and you all claim to go, oh, we found $10. No. Okay? That only works if you're the federal government. No. And since we're not, we have to work within reality. If the no, there's an honest God's truth to that. So if I've got $3.72, that's all I can lose. You okay?
Yeah.
Allergic to momentum or what?
Yes.
I hate it when that happens.
Wait, you
I
were
would-
sneezing?
Yeah.
Kim,
What?
so
Cat?
how come those two momentums added together doesn't equal?
No, these are the changes in momentum.
Oh, changes, got you.
So
Okay, and they're not gonna add up to equal to 0
Okay.
because I had some momentum that I carried into the system. Now, let's just say that took 0.2 seconds for this to occur. Okay? From the time that the bullet hit the block until it reached the final velocity was 0.2 seconds. Okay, 1001, about that long, which is realistically about how much time this is going to take. So, if that's the case, if I know the time, can I find the force exerted on the bullet?
yes.
Yes, because what else equals change in momentum?
FT.
Force times time. Right. So, since force times time equals change in momentum, right? And it also equals mass delta V. And we've already done this side. We use this side to get the change in momentum. So now I can take that change in my momentum and divide that by time to get my force. So in this case, I'm going to take negative 3.72 Newton seconds. So somebody take negative 3.72 and divide that by 0.200 seconds.
18.6.
What'd you get?
18.6.
Negative 18.6
Yeah. Yes.
Dude,
newtons. Now, why does it make sense that the force exerted on the bullet works out to be a negative number?
Because
Because
it's
it's
stopping.
that way. It's slowing it down.
With what type of velocity?
Positive.
Positive velocity. So the bullet's coming in this way. The force exerted on it has to be acting in the opposite direction, which is going to be a negative value. Okay? Seem reasonable. So, that's the force exerted on the bullet. So this is force bullet. So, if I look at the force exerted on the block, guess what? That's going to be 3.72 Newton seconds divided by 0.200 seconds. And oddly enough, I get
18.12.
positive 18.6 newtons. Why?
Has to have
That's the-
force exerted somewhere else.
What's Newton's third law? For every force,
There's an equal and opposite.
okay?
force.
So here's the deal. Look at the times. Are the times going to be the same? Yes, if I walk up to McGriddle and punch him in the arm, okay, for 0.2 seconds, guess what? McGriddle is pushing back on me for 0.2 seconds. I can't push on McGriddle longer than he pushes back on me. So the times have to be the same. So this is the beauty of Newton's third law, is that you actually prove it by the change in momentum. So because my changes in momentums have to be equal and opposite, and the times are the same, guess what? The forces have to be equal and opposite.
Well, how come it hurts Shively more when you punch him than it hurts you?
Because he's
Whoa. See, that's a question. That's a question right there.
part
See, why don't you-
part of that is for me, it's distributed over, it's hitting my bone,
Yeah.
okay, where it's hitting his muscles, so it's going to have more nerve endings in it.
So then how come when
That's
like
biology.
Ethan Farney headbutts somebody, it doesn't hurt him,
Because he's an idiot.
but it hurts that other
Because his
person?
skull is 9 inches thick.
And it's a function of nerve endings,
Yeah, true.
okay? Yeah, if I punch you in the nose where you have a whole bunch of nerve endings, that's really going to hurt.
Yeah.
Okay?
About that.
All right.
Oh my
Now,
god.
here's the
Right.
force exerted on the
Dude, no.
bullet. Here's the force exerted on the block. Could I find the acceleration of the bullet?
Yes.
You know the force acting on the bullet.
You know the mass.
And you know the mass, you can find
Acceleration.
the acceleration. So I want to find the acceleration of both. I want to find the acceleration of the bullet, and I want to find the acceleration of the block. So the force of the bullet was what, negative 18.6? So somebody take negative 18.6 newtons and divide that by 0.015 kilograms, and then we'll take 18.6 newtons and divide that by 1 kilogram, and oddly enough get 18.6. So what's the acceleration of the bullet?
Negative 1,200.
Negative what?
1,240.
Meters per second squared. Ah, now, are the accelerations equal and opposite?
No.
No. So, they're not. They're vastly different. So here's the question. How did these two accelerations, one at negative 1,240 and the other one at 18.6, how does that fit in with that velocity time graph?
They're the slopes.
Oh, those are the slopes. So the slope of the bullet line is going to be negative 1,240 meters per second squared. The slope of the block line is going to be 18.6 meters per second squared. So here's there's three things I want you to remember out of this problem. What do you know about the changes in momentum in any collision? They're going to be equal and opposite. What do you know about the forces? They'll be equal and opposite. Are the accelerations equal and opposite?
No.
No. Okay? The one with the smaller mass will have the bigger acceleration because they have the same forces. What's the only way the accelerations can be equal and opposite?
If they have the same mass.
If they have the same mass. Okay? So here's what's always true. Momentums equal and opposite. Forces equal and opposite. Accelerations, not so much. Okay? Now, let's go to the back for just a second.
2 field trips in your day. 48 plus whatever was earlier. Oh, man.
Yeah. Okay, no, you can go.
Oh, hey, I can set this down. There's a lot of vibrations.
Yeah, no, I saw you. You were so awake.
You look so sciencey.
You look so awake now too.
Hey, quit moving that.
You don't really hear that.
Ew, that's wet.
Okay, so here's what I've got. I know what he didn't have those.
Mr.
Okay.
Juice.
So I've got two different polars. When this one hits, okay, pretty bouncy, okay,
Wow, science bouncy balls.
but when this one hits, it just goes, okay?
It's sad.
So one bounces and one kind of goes. So I'm going to take this, lift it up to about yay, I'm going to drop it. Okay? So when the ball hits the block, does it create is there a force involved?
Yes.
How do you know?
Movement.
Now, I'm going to take this one and do the same thing.
Whoa.
Whoa.
No.
So,
Oh, that makes sense.
why?
Okay, so the ball is bouncing this way, so the block has to move this way, because with that one, the ball's not, rookie mistake there. With the first one that doesn't bounce, it's not moving at all. The block shouldn't move at all.
Okay? Because the momentums have to be. So here's the question. When this one bounces, okay, this one bounces, it hits, and it bounces all the way back. So this one, if you think about it, changes direction. So what does the velocity have to go through to change direction?
Zero.
It has to go through zero. So this one has to be brought to a stop very quickly, goes to zero, and then projected backwards. So when it projects backwards, what do you know about the sign of the velocity? Changes. So this one has to go from like positive to zero all the way to negative. So this thing has to undergo a huge change in velocity because it's got to go all the way through zero. This one pretty much just stops, and that's about it. Okay? So this one just goes from positive basically to 0. This one goes from positive all the way to 0 and then projected back the other way. So which one undergoes a greater change in momentum? The one that hits and stops, or the one that bounces?
Bounces.
The one that bounces, because you have to stop it and project it all the way back in the opposite direction. So anytime something changes direction, that requires a lot more force and a lot greater change in momentum than something that just hits and stops. Okay?
So does the block change direction then?
Oh, it doesn't change direction, but here's the deal. So the reason that this one knocks it over, I'm saying that. Hold on. I broke it.
You broke
It's because that takes more force to project it back, therefore that exerts more force on the block. Because the forces have to be equal and opposite.
Yes.
Got it? Good? Back we go.
I'm so tired.
It's had to say something there.
Stop.
What's in there?
His science stuff.
Were they thinking to go beat him in the back room or something?
Good bird whispered in my ear.
What'd you do, Clark?
Okay.
Thank you. Hey, there's space answered on your Max.
Is there really? The answer, the questions are spaced out. It's just like,
Okay. One more time. Or are we still going?
Yeah, we're still going.
Okay.
I'm trying to get to an hour. So.
All right, so here's the deal. So Michael had brought up something, and it's a similar type deal about like why if you just land and stop. So let's say you jump off the table, right? And you just land and you stop. Okay, all you're doing is taking your momentum from some value to 0. Now, if you land and then jump back up, okay, why is that going to require a lot more force than if you just land and stop?
You have to push it back up.
Yeah, because you have to project yourself back up. So you have to completely bring your momentum to 0 and then make it change direction. And that's why that requires a lot more force, which is the exact same thing that happened right there. Okay? Because anytime you change direction, that's a big change in momentum. Now, when you get to number 2, okay, the external force changes momentum, and how can the internal force of a car's brake bring a car to rest? So, when you talk about momentum, there's 2 general types of classifications, internal forces and external forces. So to answer the questions, let's actually start with the balloon. From a momentum standpoint, what gives the balloon its shape?
Shape?
What gives it its shape? What's this?
Molecule, like
Air getting out.
Volume
The molecules are doing what?
bouncing together.
They're hitting the sides and they're doing what?
Bouncing back.
They're bouncing back. Oh, guess what? That's an internal force, right? And this is happening billions upon billions upon billions of times a second. And that's what gives that balloon shape. So that's an internal force that's giving the balloon shape. Now, but if you're going to actually make the balloon move, what do you have to do with it?
Push it.
Yeah, you got to give it an external force. You got to give it a push, right? So if you think about your car tires, quick lesson in automotives, inside your car that's attached to your axle is called a rotor. Okay, and on the outside of the rotor, there's something called the calipers. Okay, the calipers are like your fingers. Okay, so when you hit the brakes, the calipers squeeze this on this rotor. This makes the wheel slow down. Okay, that's an internal force. But here's the question. Is hitting the brakes in and of itself enough to stop your car?
No.
Because if you've ever done that on a sheet of ice, what happens?
You slide.
You just keep going. So the brakes provide an internal force to stop the tires. But it takes the external force of friction to make it actually slow down. Okay, so there's your lesson in automotive. When you get down to number 10 is old school. It has a frictionless inclined plane. You might have to look at force parallel, force net, okay, kind of old school on that one. So basically it's going to slide down a frictionless inclined plane. It's going to hit another block at the bottom, and then they're going to do the California thing and move off together. Okay, and then also when you're going to get friction. So there's no friction, they move off together, there's friction. When you get to number 11, you have 3 astronauts of equal mass, Huey, Dewey, and Louie. And they're floating in empty space, right? Huey's at rest, pushes Dewey towards Louie, who's also at rest. So basically, you're going to figure out what's going to happen to the dynamic of this situation. So keep in mind, momentum has to be conserved even in deep space. Okay, I'm done. You're on your own.
So if I shift in space, right, wouldn't I get pushed back in the opposite direction?
With the same velocity, if we did the same mass.
Calling me fat?
You're right, I am.
I am, but you only stopped using my protractor.
He asked me if we were in space, and he pushed me. We were going opposite directions with the same speed.
stop
I
eating
said,
my
no, it's
protractor.
like massive.
You need to stop eating all of your things that measure stuff.
Not
I'm just
Slightly. That's why I said slightly.
I'm just accepting the dad body.
Oh man.
You're just what?
He's got a sick dad bod.
I'm just accepting it.
Who's got a sick dad
You,
bod?
you got the dad bod.
I'm a daddy.
No, he is a dad.
Yeah.
We push your daddy.
Think about quicker.
All right.
I don't like this no more.
Last year at Salina, playing basketball, they had some questions about how old I was in their student section. So I did my best to convince them that I had 2 kids.
Use his body.
Epic. That's so epic.
Miracle Bowl.
Yeah, I'm 92.
What was the momentum and speed of the
Really gonna much ride this race.
The same as the cube?
It looks like an indoor shot.
Did the ball stop? I do not. I do not want to. Fuel is at rest. It's the same as the
initial momentum.
Oh wait.
Photos of his girlfriend.
I got Matt's.
For you, I appreciate you.
Shauna's girlfriend appreciation post.
Oh, his cousin?
Oh no!
so
Stop.
weird.
We flamed
Dude,
him so
Shauna
much.
came in the other day. Pretty sure it was on Friday, and he's so pissed. He was like, "Can't believe Eli just told her she's my
Yeah.
cousin. She's 14. She's not my cousin." I'm like, I really don't think anybody was
No.
actually believed him. It was like,
He was so butthurt. He gets butthurt at everything. Dude, we're so mean to him, honestly.
yeah,
I mean, it's a shot.
you are.
Oh man, we only got. Eli, you should definitely not do that. 69. We got 30 seconds left.
At that point, should hit a little.
Give him a neck. What are you doing? Oh, 15 seconds. Whoa, wait, scoot over. We gotta end this on a good note.
Berg, your tie doesn't match.
What do you mean?
Since when do?
Cindy
It
Gray?
matches.
Gossip Gray.
Okay, then the eagle throws it off.
It's got red, and then there's red.
But there's like blue and there's green.
You
and
told
like
me
a weird
colors
gold
can't
color.
go together?
Which